Okay.
Can you repeat the quantum pointers?
Quantum? Yeah, I'm going to repeat everything. I'm going to recall the whole thing. Okay. So this is the second class. So, okay. So let me recall what we have been doing. So, okay, what we have been doing is we are generalizing the classical probability setup, the classical probability framework into quantum probability framework by by allowing non-commutative observable, whatever we mean by that. And the basic idea is we want to accommodate quantum mechanical model. So we want to have this quantum probability, which is a bigger framework, which contains this classical probability and then quantum mechanical models. See, what was happening was people were using probability in obscure manner to do quantum mechanics. But then the this quantum probability as a mathematical field came later. Okay. So this is a much broader framework which accommodates the quantum mechanical models and also classical probability. Classical probability is contained there, but it's a mathematical model. It's much bigger. I mean, it's not just, the idea is not just to allow quantum mechanics or something. It's a mathematics. Okay. So we allow much more, many different things, very interesting mathematical objects we will create and use, because that is the idea. So to do that, how we did. So let me recall how we did that. So so we use only finite probability space. So let omega, I called omega script of P is a classical probability space. I hope you can see. Okay. Probability space. Okay. By this we mean omega is just a set and script f is a, I mean, for us, for the time being, it is just a finite set. Okay. Finite set, which is called as sample space. Okay. Sample space, and script f is the algebra. What I mean by algebra is, I mean, usually an algebra of elements is you can add things, you can multiply things, you can multiply scalar multiple. Here you can take, this is algebra of sets, you can take union, you can take intersection, you can take complement, and the whole set is there, something like that. So it's a different algebra. It's called Boolean algebra or something. Okay. So algebra of sets, Boolean algebra of sets, okay, which are called events. Okay. This is a yes or no questions, and P is a probability measure which is from here to 0, 1. Okay, which satisfies the condition P of omega equal to 1, P of the empty set equal to 0, and P of A union B equal to. There are more conditions, but since we are dealing with the finite set, so it's if omega is just a finite set, we don't have to worry about it. I mean, it has to be, otherwise it has to be countably additive or something. So we are only dealing with finite set, so which is just P of A plus P of B if A intersection B is MD. Okay, if they are disjoint, then it is additive. So this is the classical probability space, and any finite classical probability space, any finite probability space is given by finitely, I mean, finite probability space is given by these numbers P1, P2 up to Pn, which are in 0, 1, which are numbers between 0 to 1, such that summation Pi equal to 1. Okay. And the probability is defined by P of any A equal to, I mean, if omega equal to 1 up to n, and A is contained in 1 up to n, this omega, then P of A equal to summation I in A Pi. Okay. So this is the, so we associate probability for sets, and then we get this Pi, I mean, P of any A. So this is actually given by n numbers which are greater than or equal to 0, less than or equal to 1, such that summation Pi equal to 1. So the probability of omega is 1. Okay. So how did we generalize to the, the non-quantum probability? So we have this omega script f, you don't even script f, let me see, to an algebra A and a phi. Okay. Where A is this algebra of all functions from omega to C. Okay. And phi is from A to C, which is defined by so this is f is all functions. I mean, it's a finitely many, I mean, it's a finite set. So it's a finitely many numbers. Any function is just a finitely many numbers. So this comes all the time. So any phi of any f is summation f of I pi. Okay. That's all. So this is also called as expectation or something, but I use phi because I want to call it a state or something. Then this is an algebra. Okay. I have already said what an algebra is. It's a vector space as well as a ring where you can multiply things. You can multiply, scalar multiply, you can add, and it satisfies distributive law and all that. This is an algebra of functions. And phi is a state, phi satisfied, phi is a state. State on A. That is, phi of 1 is 1, phi is linear, okay, and phi of any f star f, f bar f, if you want, you just multiply. Okay, that is greater than or equal to 0, which is clear, all those things. Okay, so this is what is state. So using this idea, then what we do is we started with omega script A, script F. We started with omega script F P, and we got this script A phi, and then we took this. We got it as pi of, I just embedded as a diagonal matrices. Okay. Matrices, and again I call it as phi. I mean, I should have called it here, but it's okay. I'm again calling it as phi only. So we just take the f1 up to f1. We just embed into the matrix algebra as diagonal matrices. Okay. So then we can get back when we have this, we can get back the script f equal to script f. We can get back by this 1a. Okay. You just say where all those. We want to get back the script f all sets, but that is just all 1a. Okay, a in script f, and that is equal to all those p in this pi of a or something. This map is pi. Let us call this pi. Then pi of a, where p square equal to p star. Where star is the adjoint matrix in the complex in Mn, and p equal to p star equal to p square. So if you take all the projections, that is precisely all these 1a, and then we got back the set. And the probability also we get and p of a equal to phi of 1. Okay. So this is the idea. So now you replace, now you call quantum probability. The definition, a quantum probability space. I'm just recalling what we did last time. Is an algebra, is a tuple, no? TUPLE, right? Tuple script A and a phi, where script A contained in MNC is an algebra, is a subalgebra. Okay, and phi from A to C is a state. That's all. Okay. I'm going to explain what it means by events, what it means by how do we associate probability, all those things. Okay. So, okay. So what is state? So that is state. I will say what a state is. State means that is phi of 1. The identity element has to be there. This is a algebra, means it's a unital subalgebra. It has identity in that unital subalgebra. Unital, if you want, it's a unital star subalgebra. Let me call it unitals. I mean, these things I said in the last class, so I'm not explaining everything. Star subalgebra. Star subalgebra means A is there, A star is there. Some A is there and adjoint is there. Unital means the identity element is there. Okay. So then phi of, this is general. It's not diagonal matrix anymore. Okay. Classical probability space, we embedded as diagonal matrices. Now we have its general matrix algebra, some subalgebra of M and C. So where phi is a state, phi of 1 equal to 1. Phi is linear. So the first condition should be it's linear. Phi is a linear map. I hope all of you have done linear algebra course. It's linear. But anyway, we will be doing whatever I am saying in finite dimension, we will be doing for a general Hilbert space or something soon. Okay. So phi is linear, and phi of A star A is greater than or equal to 0. Okay, and 3 phi of 1 is 1. Okay. That's all. So this is a quantum probability space. Okay. Now, so now I want to explain what are the events and what are the, now I want to give examples. Okay. So let's, well, we want to give examples. Before that, I fix some notations, okay, which you must be knowing already. So Cn, you know what is Cn? It's just a n tuple, okay. Cn and any element of Cn, I will write it like this. So if you have a, I mean, the elements in Cn, this is a Hilbert space. What I mean is the following. Cn is a Hilbert space. It's just a finite dimensional vector space over complex field n tuple. Okay, I call it a Hilbert space means it has an inner product on that. Okay, which I am going to define. So elements in C are given are written like this, okay? Where x is, if you have an x, then that looks like x1 up to xn. Okay. We just write it like this, x like this. Okay, then the inner product for Cn is written like this. For inner product is a function. Okay, it's a function. It's a function from Cn to C, which is given by, if you have a x like this, and it's y, you just write it like this. Okay, and it is in fact given by summation xi bar yi. If x equal to this, y equal to this. You must be knowing this in linear algebra. This is an inner product on this. Okay, so we have a vector space Cn and an inner product on that. Okay, then if you have any algebra A contained in MNC, you can take MNC itself. I mean, that's the extreme case. Okay, if you have a commutative subalgebra that corresponds to classical probability, I will explain it. I mean, we will derive a theorem. Okay, but if you strictly non-commutative, MNC is very highly non-commutative in the sense that something commutes with everything is identity and zero. There is no other element which commutes with everything. Okay, so which is highly non-commutative. MNC is highly non-commutative. Diagonal matrix completely, I mean, it's commutative algebra. Diagonal matrices are commutative. They commute with each other. And MNC is, of course, there are commuting elements, but nothing commutes with everything except identity and zero. Okay, so A is contained in MNC. Now I want to unfix, let's take an element X in Cn. Okay, then you define phi from A. You can take A to be MNC itself if you want. Okay, phi from A to C defined by phi of any A is equal to xi. Sorry, I have given x, no? So I should write x and ax. Okay. Okay. And one thing I want to say is, you look at our inner product. This is xi bar. Okay, and it's a conjugate linear in the first variable. Yes.
So the inner product is defined on C to the n, C to the 2n.
And C to the 2n, C to the n cross T to the, sorry. Correct. Yeah, C to the n cross T, C to the n. Okay. And one thing we have to notice is our inner product is conjugate linear in x variable and linear in the y variable. Usually the inner product is the other way. In mathematics, mathematicians have got it wrong. So the inner product is supposed to be linear in the second variable and conjugate linear. This is physicists, they got it right. Okay, so this is because if you want to use this notation, which is called Dirac notation, it's not possible in mathematicians mathematical notation. Okay, so we will use this because we want to use quantum probability, we want to use that, so we will use the physicist notation here. Okay, but one thing I'm very sorry to confuse, when we do the other class, which is a mathematics class, graduate analysis, where we are sharing something for 1 month or something, some 4 or 5 classes we'll share. There I will be using the other inner product, but I will mention it and I will come back to this. Okay, later. I'm sorry about it. Right? There is no confusion. It is just when we want to use this notation, this Dirac notation, right? Inner product like this. Okay, then we need this. The reason is the following. So this is a phi of A. Okay, so there is another condition. You have a vector. You have a vector X in Cn, and this should have norm equal to 1. That is norm. I will also call it just X. Okay. I will also call it norm X square equal to the inner product of X with the X, which is equal to 1. Okay. I mean, for it to be a state, then only it will be phi of identity will be 1, right? You want phi of identity to be 1. A is identity, the norm X, the XX should be 1. So because of that. Okay. So I'm just, I mean, you have a script A, which is an algebra, any algebra you can take. If you want, you can take M and C itself, Mn itself. Then you define a phi from A to C by this prescription, the inner product XAX. Okay. This is a state. You can verify that this is a state. Why is this a state? Because if you have any, so we want to, so clearly phi of 1, phi is linear, clearly, because the inner product is linear, the second variable, phi is linear. You fix X and it's linear in A, right? This is a linear map in A. And phi of 1 is equal to just XX, which is just the norm, which is equal to 1. And phi of A star A, if you take A star A, which is just X, A star A, X. Now you know that's the star, you can bring it to the other side. Okay. We will define all these things in Hilbert space. So we can bring the star in the other side. So which is just AX, which is equal to norm AX square, which is greater than or equal to 0. Okay. So this is a state. So this state is what is called a vector state or a pure state. I call it vector state. This is also called pure state for a different reason. There's something called extreme points. These are all what are the extreme points of the collection of all states. Since I haven't introduced the notation, so I'm not calling this pure state, but this is also called pure state. But the pure state has a different meaning. But these are the pure state. You have to prove that these are actually the pure state. Yeah.
So for every X which is normalized, we get a state.
Correct. Yeah, you get a vector state. So that is why this Hilbert space Cn is called a state space. Okay, this is a vector state, but there are more states. Okay, these are all called vector states or pure state or something. There are more states. I will come to that in the next example. Okay, so this gives vector states. Okay, so this is just an example. Okay, so what else we have to notice? There is nothing to notice. So this gives a quantum probability space. Okay, A with this phi is a quantum probability space. Okay. 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 If my handwriting is fine, I will send this notes to you later. Okay. I mean, if you can read it. Okay. So there are each year some student complains that my handwriting is bad, but I don't think I can correct it at this age. Okay. So I'm sorry. What? Yeah, I'm fixing an X, right? X is fixed, A is variable. You fix an X. For each X, you get a state, vector state. Okay, so then the next example, I mean,
What is A star? I just forgot.
A star, which is just take the transpose. A is a matrix, bar of the transpose.
Oh.
Take the bar and then conjugate. It is called conjugate otherwise. So you are in BSc for which year? Third year. Okay. So, but okay. In linear algebra, you must have seen it that. Okay.
Yeah,
But you.
We less of the
Okay. Okay. No problem. This is just the conjugate. Okay. 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 So this gives a quantum probability space. The next example is where is the, so initially I fix the notation, then this is the example, right? This is the example. Okay. This is example 1. Now let me do the example 2. Before that, I want to fix some more notation. Okay. So I define this trace from M and C to C given by trace of any A equal to summation AII. I mean, this is just it's just a matrix, okay, for A in M and C. Take A in M and C, just the sum of the diagonal elements. Okay. Then you can notice that trace of AB equal to trace of BA. So it's known, we can directly verify it. Okay. Trace of AB equal to summation AB II, right? I, okay, which is equal to summation A, I, J, B, J, I, right? With I and J, it's just the product II. So which is also equal to summation Ij, Bji, Aij. I'm just commutative numbers. Okay, they are all just matrix entries, the numbers. So which is same as summation J and I, Bji. So Bji, this is just which is just B8th thing of Jj, right? I has gone. That is just the Jjth entry of BA. Okay, so that is equal to trace of BA. So trace of AB equal to trace of BA. A and B need not commute, but any AB, trace of AB equal to trace of BA. So you should remember that you can't, I mean, you can't change positions of, if you have a finitely many matrices inside trace, you cannot change position. You can only come circular, something like this. Trace of ABC equal to trace of CAB. And you can bring it as equal to trace of CBA. It's like this. You can bring the one in the left to this side, something like this. It should be BCA, correct. Sorry. Yeah, it should be BCA. You can bring the BC, correct, right? You can only bring one the left to the this side. Okay, that's, I mean, any number of things. AB you can bring it if you want. You can do anything. Okay, that's all. So trace of AB go to trace of B. Not that everything commutes inside or something. It's not true. So this is the trace, and trace is a linear functional. Okay, I mean it's linear. Okay, trace of lambda A is lambda times the trace of A, and trace of A plus B is trace of A plus trace of B. So now, for example, next example for quantum probability space, what is trace of identity is n.
Yeah, but they require it to be one.
No, we will use some density matrix, so it will be okay. Okay, so let rho be this is what is called density matrix. Okay, that for that I will use trace, small trace. If I normalize it by 1 by n, then that is called small trace. Okay, so now rho be an MNC. Okay, such that this is called a density matrix, such that rho is greater than or equal to 0. That is any x rho x. This inner product is greater than. This is the definition of positivity. Okay, I mean these things we will define in a much broader setup in a Hilbert space for operators. Okay, here if you don't remember it in the linear algebra, this is the positivity. Okay, the positivity, the condition is this. Okay, x rho x is greater than or equal to 0 for all x. Okay, for all x. This is what is called positivity. So the it's positive and trace of rho equal to 1. Okay, so a positive matrix, positive automatically implies it's self-adjoint. Okay, it's a self-adjoint matrix, that is A equal to S, rho equal to rho star. A positive matrix with trace 1 is what is called a density matrix. That's all. Okay, so if rho is a density matrix, then on MNC you can define it on any A also if you want, which contains identity. So if you have a density matrix, then you can define. I said that is rho is positive, means this x rho x is greater than 0. Okay, that is the definition. Then define phi from MNC to C by phi of any A equal to trace of A rho. Okay. Okay. Then we can verify the following. Phi is linear, then phi is linear, of course, because trace is linear. Okay, and phi of 1 equal to trace of rho, which is equal to 1. And the third thing is phi of A star A, which is equal to trace of A star A rho. See, here comes something which is equal to trace of. See, if you have a positive element, I will prove it later for a Hilbert space operators. But for matrices, if you don't know, please accept. Okay, if you have any positive matrix, then there is something called a unique square root, which is also positive. Square root, there are many square roots. Okay, for a positive, but there is a positive square root is unique square root. Okay, that is what I call it as rho power half. So you can write, I mean, if you for positive A in MNC, there exists positive A power half in MNC. There exists a unique positive A power half such that by A power half square equal to E. Okay, so I call that as A power half. Okay, then this A rho can be written as rho power half square. Okay, so which is equal to A star A rho power half rho power half. Okay, now this is equal to trace of rho power half A star rho power half.
Sir,
Yeah.
so in the definition of square root, we would also require the a power half to be a positive.
Yes, unique. I mean, I put a comma, no ditto. That's you. This is my symbol for unique.
Yeah.
That's my symbol for you. Oh, I should have put here. Okay, I should have put here. There exists a unique. This is also I mean, I was just lazy to write positive again. Okay. There exists a unique positive such that this happens. Because of that, our original trace A star A rho will become rho power of A star rho power half, which is actually looks like this, which is equal to A rho power half. A star, you know. So I'm sorry, this should be A star, that should be A. I'm sorry, right? Because A star is here. So which is equal to A rho A star A rho star half. Now trace has the following property. If you have any, I mean, what is trace? Trace is trace. I mean, trace of any B star B equal to summation EI. EI is an orthonormal basis of something. A star B star B, no? B star B EI, right? That is equal to summation B EI, right? This is the trace, no? Trace is sum of diagonal elements. Diagonal elements are nothing but inner product of EI with BEI, right? That is how the matrix element is defined. Huh? Here. A B star is B star A star. Rho power half is self-adjoint. So rho power half star is star. Sorry, it should be rho power half. Sorry, I forgot. Yeah, star of that. Star I have written. No? Star is no rho power half is star. Rho power half star is star because it's positive. Positive things are self-adjoint. Self-adjoint means star is itself. Okay. We will, I mean, this is just the example I'm giving in finite dimension, but we will deal all this positive operators. We will do a whole Hilbert space theory where we will define all these things. So if you have some problem now, you don't worry. I mean, you accept it now. Okay, this is just to show you the examples in finite dimensional case. We will be dealing with Hilbert space, infinite dimensional objects. We will be dealing with later. Okay, so I will define all these things. For the time being, I am assuming all this linear algebra stuff. Okay. Okay. So if you have any trace of B star B, this looks like some B star B, right? Some that is B. I mean, this. So now I am saying that any trace of B star B is positive because it looks like summation norm B EI square, which is greater than or equal to 0. Okay. So our original fee, see, we started with phi of A star A. Phi of A star A is trace of A star A rho. Okay. Then we used the square root property and we got this. Finally, we wrote it in some of this form, trace of some B star B. A trace of B star B is positive for all B. Okay. Here the B is this. Okay. Is it clear? If you're not clear, you ask me. Okay. So this is greater than or equal. So this says it's a state. So now this phi MNC with this phi is a quantum probability space. Okay. This is an example of quantum probability space. So now I want to say that every quantum probability, every state on M and C will look like this. Okay. So that's what I want to say. This is the example. Given a density matrix, given a matrix rho which satisfies the condition, rho is it's a positive operator or positive matrix, and such that the trace rho is 1, then we can define a quantum probability space by this prescription. I mean, we take M and C and then we define phi to be trace of A rho like this. Okay. So then we get then phi is a state, and that is a quantum probability space. Okay. Now I want to say that. So you want to write something? Shall I show you something, or you want to see the screen or something? I will send you this notes if you can read my handwriting. Okay. So, okay. Now I want to say that every quantum probability space with A as M and C will look like this. That's what I want to say. So this is the converse. Maybe this is a theorem. Okay, call it a theorem. So what is the theorem? If M and C, phi, and maybe I will not say. I will say phi is a state on M and C. Okay. Phi is a state on M and C. Okay. Then there exists a rho in M and C, a density matrix. By this, I mean it's a positive matrix with the trace of rho equal to 1. That's what I call it as a density matrix. Okay, that is density matrix. By this, I mean rho is greater than or equal to 0 and trace of rho equal to 1. This is what a density matrix is, such that phi of A equal to trace of rho A or A rho, doesn't matter. Okay. So why is this true? For this, I need what is called Ree's lemma. If you have any finite dimensional vector space, the dual, the set of all linear functionals on that, is itself. Okay, and that is given by inner product. We will be proving this for a general Hilbert space in the next 2 classes or something. But here I am assuming for finite dimensional spaces. Okay, I will be using this here. Proof. We have M and C, which is a vector space. Okay, I identify this with Cn square, right? This is Cn square. Now Cn square has an inner product. Okay, and any linear function on Cn square is given by that inner product. Okay, if you have any inner product space, I mean it's true for in general, any inner product space also it's true. If you have any, I mean, if at least you should be knowing for finite dimensional space. If you have Cn, for example, any linear function. So suppose, I mean, this is a fact. Maybe I use a different notation. Phi it will come, I think. It's because of, but my video is moving, screen is frozen. Okay. Wait a minute, let's see. It's fine. Okay. So the fact is, if you have a phi from Cn to C, okay, a linear functional, then phi is given by there exists a x in, then there exists a x in, maybe like this, x in Cn, such that I may write like this Dirac notation, or just write x. Okay, both are same. X in Cn such that phi of any y is given by xy. Okay, for all. Okay. This is a fact. This is what is called Ree's lemma. Okay. We will prove this later for a general infinite dimensional Hilbert space. Okay, we will prove it later. This is for finite dimensional. I mean, you must have seen any dual of a finite dimensional vector space is itself. This is true for any finite dimensional vector space. And it's when you have the inner product, it is actually given by this. Okay. I mean, any finite dimensional vector space are isomorphic as algebraic isomorphism between them. And you can bring the dual here. Okay, whatever. Okay, so it's enough to do it for one such space. Okay, now this M and C, you have Cn square, and you have the, you know that Cn square, it's dual. Any linear functional is given by a vector in Cn square. So that is also given by a vector in, so for any linear functional M and C is actually given by another matrix. Okay. From matrix, you can go to Cn square. From Cn square, you can come back to the matrix. Okay. So there exists, so there is so phi is a state, phi is a linear functional. Now phi from M and C to C is a linear functional. To start with, it's a linear functional. I am saying it's a state. Okay. First, it's a linear functional. So this implies there exists a maybe rho, call it rho in MNC such that phi of any A is equal to summation A ij rho ij, right? Aij bar, maybe bar, there is a bar somewhere, rho ij, it should be bar is here. Okay. So now this is equal to, what is this? If you just write it in a different form, this is equal to summation. I mean, summation is over ij. Okay. So which is aij rho j I bar. No, rho ij bar, sorry. Rho ij bar, which is just rho star ji. Rho star is rho, so it doesn't matter. Rho star of rho of ji. Right? I mean, if you want rho star, I mean, rho star is a bar of the transpose. So it doesn't matter because rho star is rho. Okay, so that doesn't matter. So this is just summation of A rho II, which is equal to just trace of A. Okay. So we have, so any linear functional on the matrix algebra, M and C, is actually given by a rho, by this trace, using this trace. It is indeed the case that if you have A, B in M and C, then this you can get this inner product. AB equal to trace of A star B is an inner product. Okay, I am just using this fact. Okay, it is in fact the sum. I mean, it is the same inner product on Cn square. Okay, it's the sum of all those Aij, Bij.
The reason does that there is a row, but does that also that row is positive?
No, we are going to get it. Yeah, we just got a row. Okay. Now we want to prove the other way. We want to prove few things.
Sir, so to use the row is rho star, we need that it's positive.
Ah, good. So then we will put it as rho star. Okay, no problem. A rho star. Good. Okay, A rho star. Now there is a row such that A rho star. Good. Sorry. Yeah, good. So now we will prove it's positive. Okay. Now trace of any. So now we want to prove it's positive. First thing is trace of identity is 1. Sorry, phi of identity is 1. Now phi of identity is 1. This implies trace of this row equal to 1, right? And then you want to now phi of any A star A is greater than or equal to 0. Okay, this implies trace of A star A row is great. We got rho star. Okay, rho star is greater than or equal to 0, right? Huh? Say rho star only. Trace of rho star is 1. Okay, good. No problem. If I can take rho to be rho star and keep it rho or something. Anyway, it's okay. Rho star. Let me call it rho star. And now the point is take A equal to this. This is an operator. You know this operator? This A, I mean this operator acting on any Y, X, acting on any Y, Y is a vector like this, which is just X, Y, which is inner product XY, which is just a number. You can bring it. It's just this. This is what is called rank 1 operator. Rank 1 matrices are on there. Okay. if it acts on an element, takes the inner product with that and multiplies with the other vector. I mean, a rank one operator. So this is in, I'm assuming all these things and going, but we will be defining all these things again when we do for Hilbert spaces and other things. Okay, so please don't worry about it. But maybe I will write it rank one operator. Maybe I will define it here. Again, I will define completely.
We fixed an x.
Yeah, fix an x. Yeah. So for example, let's fix x and y. Okay, x and y in Cn. Okay. Then you define this operator, define this operator, define xy. You can define, this is an operator from Cn to Cn. Okay. This is what is called rank one operator, where xy acting on, this is an operator acting on any z is equal to y z, the inner product times x. Okay. You just compose the whole thing. So this is where you need this, the mathematics, mathematicians notation will not work here when you want to use this. Okay. So here if you say you can just compose y and z, you can't do it. You have to write it in a different way. Okay. This just y is just an inner product, which is a number. You can bring it to the other side. The number will commute, and it's just the number times x. This is what is called a rank one operator. Okay. The range is just one dimensional, which is just the span of this x, cx or something. Okay. Span of x. It's a one dimensional. The range is one dimensional. Okay. So now you take A to be this xx. Okay. Now trace of, there are too many things to do. You have to verify that A star A is A itself. Now A star A is equal to, exactly, and x has to be norm one. X has to be, no, you don't need it here. You want to, x is norm one, we don't need. It can be 0, then it will be a 0 operator. Okay, we take this. Okay, then A star A is just norm. I mean, what is A star A? You want to use A star. So I have to, so for the time being, you take it like this, okay? Because I will be doing this again for a Hilbert space, so I don't want to repeat. If you have any operator like this, xy, then its star is going to be yx. Okay. Okay, please assume this. So xx, the star is xx itself. Okay. Now A star A is, so if you have xx star xx, okay, then that is just going to be norm x square times xx. Please take it for granted. You can try, sit and work it out. Okay, it's very easy, and leave it as exercise. Now, so this is the xx star xx. Now, if you take A equal to this, then trace of A row or A row star, if you want, whatever, that is equal to trace of A star A. Yeah, A star A. You want to find this. So this should be greater than 0. So this is just equal to, I'm just saying that, see, the point is, the trace is just the sum of the diagonal elements. So there is one thing, I mean, the trace does not depend on, I will prove it later. Trace does not depend on the orthonormal basis. See, the trace, or you can see, if you are comfortable with linear algebra, I will explain. So the trace of anything does not depend on the, see, if you have one orthonormal basis, to get another orthonormal basis, you apply a unitary. Okay. If you have a matrix is something, it's a linear operator, but matrix is written with respect to an orthonormal basis. If you want to write the same matrix with respect to an orthonormal basis, you take a unitary operator, which takes one orthonormal basis to another orthonormal basis. Then the new matrix is actually given by u star AU. Now, if you apply the trace of this, that is just trace of u star A, but u star is 1 for unitary, so which is same as trace of A. Okay. So in particular, trace, this function does not depend on orthonormal basis. Orthonormal basis. Okay. you can take the trace with respect to any orthonormal basis. And these things I will go through it again for a general Hilbert space. So this is just to explain you, I mean, give you the how the proof works. Okay. I mean, even this trace, this whatever the theorem I'm proving, this also I will prove for infinite dimensional. Not in, I mean, this is not generally true. We need to use something called trace class operator. I mean, you can't take any operator like that. You have to take some trace class operators or something. We'll do it later. Okay. So because of that, if you have, you can see you have a x here. This A is given by Ax. Okay. You fix the first vector to be X, and then you can extend to an orthonormal basis. Okay. You know, Gram-Schmidt orthogonalization or something. You start with an X, then you get an orthonormal vector to X. Then you so another vector starting with this, and only finitely many of them. They are all linearly independent, and you will exhaust after some time. Okay. So you get an orthonormal basis starting with any X. So you start with that. Okay. You so take orthonormal basis starting with X. Okay. Then the trace of this, trace of A star, A rho star, whatever we got, which is nothing but trace of norm x square times again xx only, xs times rho star, whatever. Now this is equal to, you want to apply this norm x square, you can take it out. That's a number, positive number, you can take it out. This is just, you have this. You take an orthonormal basis starting with X. Okay. X, and then you want to apply this norm X. I mean, let me have this row on this side and X on this. Trace, you can keep the operator whichever the way you want, acting on this X, right? So you will get norm X square times another norm X square if you want, times X rho X, right? This is what you will get. Now phi of A star A, which is equal to this, greater than or equal to 0. This is greater than or equal to 0. This implies X rho X is greater than or equal to 0, which is the meaning of rho greater than 0. Okay. So we got rho to be greater than 0. I mean, we want star, rho star, okay. I mean, initially I could have taken rho star, doesn't matter. Okay. So rho is greater than 0, same as rho star is greater than 0, it's the same thing. Okay. So I have proved that if you take any quantum any state on MNC, that is actually given by a density matrix. A matrix which is positive, whose trace is 1, and that's all. Okay. And by this prescription, phi of A equal to trace of A rho. Okay. So to get states, we only have to worry about density matrices. Okay. Whatever we call it, density matrices. Okay.
For only states of the
whole MNC. Subalgebra, you have to consider the dual separately. I mean, if you have a subalgebra, then there is a theorem, something called Veddervan theorem, which will say that it will be direct sum of matrix algebras inside that. Okay. I mean, I will not go through all that. Okay. Then you can compute the dual inside that. That will not be uniquely given by one state or something. Here it will be, because this is something called, we see this MNC is highly non-commutative. So if you have direct sum, then the commutant will be different. So there will be some problem up to something you will get. See, this A is unique. This A determines the thing. There may be more than one A in that situation when A is not what is called a factor. I mean, what is that? The center is trivial, no? For MNC, if the center is not trivial, then you will get more than one A determining one state. Okay. So, but then you can compute the dual and write it. Center is, that's trivial means, I mean that. Okay. It's only scalars. That's what I mean. Trivial means it has only one and 0. Okay. So we have got all the states. So let me discuss events and then come back to whatever the coin tossing or whatever. Okay. So now what are events? The classical probability space events are sets. Okay, just subsets. Of course, if you have an infinite probability space, then the set has to be what is called measurable and all that. If you attend the course on measure theory, then you will know it has to be measurable or something. But since it's a finite set, we don't have any set. We can deal with any set. So the events are set. Okay. So events in the classical probability space, events are sets. Okay. A contained in omega. I mean, omega is finite. Okay. So I'm just taking any set is an event. So this corresponds to 1A in the algebra A. Okay. Which is actually what is called a projection in the algebra. I mean, if you consider the diagonal matrices or something, it satisfies the condition of the projection. So in quantum probability space, when you have a phi is a quantum probability space, okay, then an event is just a projection.
Classical probability space isn't an event, is the element of the F.
Yeah.
Algebra of events.
Correct. Algebra functions. You know, huh?
I mean, no, the script F you use.
Correct. But I am taking, since omega is finite, I'm taking all subsets. Okay. Yeah, if you want. Okay, maybe I will write. You are right. That's what I said. If you have an infinite thing, then you have to worry about that. Okay. Here you don't need to worry about it. You can, I mean, you don't need to worry about script F. That is just to construct the function algebra I use there. Okay? That is just a notation. You have to remember when you have the interval 0, 1 or something, you cannot take any set. Okay, you have to take only measurable set, something called sigma algebra, all those things will matter. Here it doesn't matter. Okay. So an event is a projection. Projection P in A. That is P equal to P star, its adjoint equal to P square. Anything which satisfies this. Okay. And a projection corresponds, so the MNC is our operators on Cn. Projection will correspond to a subspace of Cn, right? Which is the range of P. Okay. Are all those X in Cn such that Px equal to X. I hope you all know all these things. We will be doing projection again for regular space, the same thing. Okay, but that's the definition of projection. Okay, I mean, because classical thing, that is, we are just generalizing classical thing, no? Classical ideas. You will see why we are doing it. If when you do a random variable, because any random variable, see, if you by spectral theorem says that a random variable here is a self. See, this is just a language, I mean, a framework where we are generalizing the classical probability so that quantum mechanics can be done. What is quantum mechanics? We want to do quantum mechanics. We want to associate for position. We have to associate some operator. For what is this? Momentum, we want to associate an operator, which are not commuting with each other. Then we want to do the same probability theory. So, okay. So then the events are the eigenspaces of that. What is an event? If you have a random variable, which is just a function in the classical thing, okay, any function in this finite setup can be written as summation lambda I 1AA or something. Okay, 1AAs are the eigen projections or whatever. Okay, if you take a general random variable, which I haven't defined yet, which is the self-adjoint operator, which you can write it as summation lambda I some projections, which are called eigenspaces. Okay, those eigenspaces corresponds to the events here. See, the sample space is replaced by the Hilbert space Cn. Okay, the points in Cn are the sample space, whatever you mean. And I mean, every point gives a state, right? Vector state. So that is the sample space if we want. And here we got, but then we don't have, I mean, whatever it means, the sample space. Okay. So here we are replacing that algebra 1A by, I mean, by this projections, set of all projections in A. They are called events. Because we can associate a probability to that. Phi of P is the probability of getting that event. And the complement, for example, if you want the complement, which is just 1 minus P, which is the projection onto the orthogonal complement. If you have a space, you take the orthogonal complement. Okay. If you have Cn inside Cm, then Cn minus M, that is a, I mean, if you have a space like this, what is orthogonal? It should be orthogonal complement. Suppose this line is a subspace, then this line is orthogonal complement. Okay. So you get orthogonal complement. Okay, so an event is just a projection. Okay, okay, okay. So the main point is we say, so definition, next definition, two events E and F in script A are said to be compatible if they commute. Okay, if they commute. If they are compatible, see, in quantum mechanics, we do experiments and we ask questions. I mean, I don't know how they do all that, but they adjust the apparatus and repeat the experiments. Okay. And then you can ask questions. You can ask compatible questions. So for that, the questions are the events. Okay. So when you want to have, when they commute with each other, you can ask compatible questions. If you want to ask incompatible questions, it will not be possible because when you measure it, that will affect the whole system. Okay? The whole system will collapse to whatever you are measuring, whatever that event, which I will define it next. Okay, the measurement, the definition of the phenomenon collapse or something like that. Yeah, I will define it.
Like if you do EF whole star, you get F star, E star.
Right.
And then you already have F star is equal to F and E star is equal to E. Oh, but
E and F are positive. What do you want?
Oh,
E and F are projections. What is the question?
E and F are events, right?
Correct.
So for E and F, E star is equal to E, F star is F.
Correct.
So if you do EF whole star, you get F star, E star.
No, EF whole star equal to F star E star. No, but why is EF star is EF? No, no. No, no, no. E star, EF star is equal to FE. So it is equal to, it says that EF equal to FE. That is EF is self-adjoint. That is not true. Unless they commute, that's not true. That's what this is. Okay. EF is self-adjoint if and only they commute. That means it's also a projection. Okay, EF square, if you compute, that will be EF if you do this, right?
So can you repeat the explanation which you gave in relation to experiments?
No, experiments. No, for that I will define what. See, if you have some E1, E2, E3, En, all projections which commute with each other, okay, then you can do experiments. I mean, then you can do experiments where, I mean, you can repeat the experiment by asking these questions about E1 up to En, which are all compatible things. But if E and F doesn't commute, okay, suppose you have E1 up to En, need not be commuting. Okay. Okay. Then what happens is, if you want to compute the probability of something, some EK or something, so you first measure for E1, then you do apply for E2. What happens is, once you measure, the system will collapse to E1. What you will do, what it means by collapsing is, you have E1, then the whole thing will collapse to, if you can't measure it E2, you can only measure to E2, E1, E2. This is a projection. E1, E2, E1 is a projection. Okay. So this is what you can measure. You cannot measure E2. When you measure, that will affect the whole system. The system will collapse to E1, whatever E1 is. E1 is a subsystem. Subspace means it's a subsystem. I mean, a system means En is a system. E is a projection. If you apply ECN, you will get a subspace. That is a new system. And when you do the experiment and measure it, it will collapse to the ECN. Then, when E1, CN or whatever, when you want to measure E2, you can only measure E1, E2, E1. Okay. But when they commute, it doesn't matter. But E1, E2, E1 is just E2, E1, which is just whatever the part of E2 here, whatever the part in E1 minus E1, that is what you will get. Okay. Now the point is, so if the fact or note, maybe actually I thought you will be very comfortable with linear algebra and other things. So I was going through this. Maybe I will do Hilbert space theory and then come back to this or something. I thought I will introduce the finite dimensional ideas and go to general Hilbert space theory, because I thought you know very well the linear algebra. If that is not the case, I will do the Hilbert space theory and come back to these things later. Whichever the way. This is okay? Is okay. So far, okay. Okay. So note, if E and F are commuting, okay, then EIF equal to FIA, I equal to 1, 2. Okay. There are E1, E2, and E1, E2 are commuting with F. Okay. Then I have to define it. So you can take union of two projections. If you have two sets A and B, then you can take union of sets. Similarly, you can take intersection. You can take union of projections by the following prescription. If E and F in MMC are projections, okay, then EF equal to, this is just the projection onto the range of, onto the span of you have to take this span, it's vector space, okay, which is something like a maximum sup or something, okay. So if you have a projection E that has a range, projection F that has a range, which is subspace, you take the linear space spanned by both of them. We take all those summation lambda I, xi or something coming from all those things, okay. You take the span of those things. So that is what is called the sup of this E and F, okay. And the inf is very easy, which is just the intersection. There you don't have to worry, which is just projection onto range of E intersection range of F. Okay. Okay. Now the point is, now this is a fact. Maybe I will prove it. Just prove it and stop. Okay, maybe I will call it proposition. E1, E2, F, all these things commute among themselves, okay, mutually commute, they commute among themselves, okay. Then F, this E1, this E2 equals to F E1. This is the distributive law holds. Distributive, okay, holds. Okay. Of course, for sets it's certainly true. This is true for spaces also. Okay. That is because the proof, if they commute, okay, E1 in E2 is nothing but E1 plus E2 minus E1 E2. You can take it this definition if you want. Okay. This will be you check it's a projection. You take its star square, this will be a projection. This is precisely that. Okay. I mean, only when they commute, not otherwise. When commute. Okay. And even this inf is just E1 E2. Now, if you use that, it will be clear. So from this, it follows. I don't want this is exercise. This is exercise. You just directly write it. It will be clear. Okay. Just do the computation. It will be clear. I don't want to give it as an assignment. It's clear. Okay. It's an easy exercise. I will give a different assignment. How many of you are going to take this as for credit? All of you plan to do it? It is for free. Okay. So I will give an assignment after this. Okay. So, but this is not in general true. So, example, So I thought I will introduce counter example. This is a counter example. In general, I mean, this is what is called logic. In mathematics, logic, whatever the mathematics uses logic, that is based on sets. Quantum logic is based on this kind of projection. Okay. Mathematical usually classical logic is distributive because sets are distributed. Here it's not distributed. Okay. In general, the events are not distributed. Events do not satisfy distributed, which is just clear. That is, there exists E, E1, E2, F, such that F intersection E1, E2 is not equal to 7. I mean, 2 dimension, it's clear, right? You take this, okay, let what is the let E1 to be some one-dimensional space, E1 to be x-axis, take even, I mean, projection correspond to x-axis, okay, and E2 to be y-axis, projection onto y-axis, and you take this to be some F, okay, some diagonal, okay, F to be some diagonal. Okay. Then it's clear E1 union E2 is whole of R2. That intersection E is E itself. That intersection F is F itself. On the other hand, F intersection E1 is 0, trivial. F intersection E2 is also trivial. When you take the union, it's 0 again. So it's clear. So distributivity is not satisfied by space subspaces. Right? You take E1, E2 to be x-axis, y-axis, F to be in some other diagonal or something. Okay, then it will not satisfy the distributivity. Okay. So maybe I will stop. I will give the assignment in the next class. Okay. Because I have to catch the bus at 5. I'll stop. Okay. Thank you. So this I will take it on. So I fixed it on Monday with the MSc students, then the next class. But next Monday is holiday. We already lost one class today. So I'm thinking of having it on Friday, but I have to ask them again. So I will ask them, and maybe Friday, Friday 3:30. Sorry, 3:30. Yeah, 3:30. 3:30. Yeah. If they don't like 3:30, we'll have it at 4:45 or something, or 5 to 6:15 or something. I mean, the Monday classes is 5 to 6:15. I initially fixed at 4:30, sorry, 3:30, but then they have some tutorial, something there. Some of them are.
3:30 we have the environment class.
Okay, so then 4:45. Sir, 5 o'clock. 5 o'clock. Okay, 5 o'clock. Okay, I will. So I will check with them. Okay, if that is all right with them, we will have it on coming Friday. Okay. For this, 1 second, I will. So there is a book by. I will close this.